Hello, everyone. Thanks again for joining us in this new Porous Media Tea Time Talks session. Today, we have a very special program prepared for you. The first surprise is that we have a new member, Sara Perez, that will introduce herself now.
Hello, everyone. So I'm Sarah. I'm a PhD student in the Laboratory of Mathematics and Applications in the University of Pau and Pays de la Dour, which is located in the southwest of France. And it's for me a pleasure to have joined this team, and I'm looking forward to seeing today's presentation.
Thank you, Sarah. We're very excited to have you, and we're very happy.
Thank you very much.
see our members expanding geographically. So now I would like to introduce our first speaker without further ado. Our first speaker is Lukas Moser. Lukas holds a PhD degree from the Imperial College London. During his graduate studies, Lukas was the first one to successfully train generative models with digital rock volumes, and he showed that they were able to honor the underlying rock structure. With this, he set the bar for machine learning in porous media science. Lukas' papers are considered among the most important machine learning benchmarks in porous media, and personally, they were the main inspiration for my PhD research. Today, Lukas will be talking about, of course, machine learning, but in particular, he'll be talking about stochastic image reconstruction and inverse problems. So without further ado, Lukas, the floor is yours.
Well, thank you very much for those very kind introductory words. Before I start, I would also like to acknowledge my co-authors, Olivier de Brul and Martin Blunt, who have been my advisors during my PhD, and the presentation that I'll give to you today will cover the work that I did during my PhD. You can also find the supporting material under this QR code, which will lead you to all the references and code that supports the work that I'll show you. So just to give you an overview of what I'll present, I'll introduce to you generative models, specifically deep generative models, and we'll look at one specific type of model called generative adversarial networks, or GANs, and how we can use them for pore and reservoir scale modeling. We'll then try and condition these GANs to observations, such as well data at the reservoir scale or thin sections at the pore scale. And finally, we'll combine these with some physics and try to leverage them as a prior for inverse problems. But to start, let's cover some of the basics and what really is a generative model. Well, a generative model tries to solve the task that if we have some data, we want to create a model that allows us to generate similar data. And here I'm showing on the left-hand side the MNIST handwritten digits data set. These are 60,000 images, which are going to be our so-called data distribution, or P data. And on the right-hand side, you can see samples from a generative model that is trying to emulate the data distribution that we see on the left side. And these two distributions ideally should be close. I put an asterisk here because close is a very vague term that needs to be defined more precisely for these types of data sets. But in general, we can differentiate between different types of generative models. We can consider conventional models, which you might be familiar with, so-called mixture models, or maybe hidden Markov models or trees. But what we'll consider today are deep generative models. And these are called deep because they leverage deep learning and specifically deep neural networks. In this presentation, the main focus will be on these so-called GANs, but there are other very interesting deep generative models, such as autoregressive models or self-normalizing flows that you might consider for your modeling tasks. So how do these generative adversarial networks work? Well, they consist of two parts. We're going to try again and build a model of this MNIST data set of handwritten digits, which is going to be our P data, and we can take training examples from this. But the GAN consists of two parts. First, we have a generator, which is going to sample from a noise distribution. Typically, these are Gaussian random variables, and we can also call this so-called latent space. And we'll take one of these, a sample from this latent space, and transform it using our generator into a sample from our model distribution. And initially, this generator, of course, has no idea how to create a sample that looks like a handwritten digit. So what we need is a second model, which is called the discriminator. And the discriminator's role is to distinguish between these examples from our training set and the ones coming from our generator. Now, the key part here is that we're going to represent the generator and the discriminator by deep neural networks, which also allow us to leverage gradient-based feedback from the discriminator to the generator to be able to improve its outputs in trying to create more realistic versions of the data that we see here. And so over a number of iterations, we hopefully start to move into a space with our generator that slowly starts to resemble handwritten digits and ultimately is indistinguishable from our training data set. If we look at this in a more in a dynamic way, so what you can see here is as the scan starts to train on this data, we can see it going from random noise to an evolving distribution over handwritten digits that at some point at the end then look like a subset of the training data and really emulates the characters of these handwritten digits. In our case, Javier already mentioned it in the introduction, we trained these scans on three-dimensional images, on micro-CT images. And specifically here, I'm showing an example of what these networks look like. On the left-hand side, we input one of these samples from our Gaussian latent space. And then there are a number of so-called convolutional layers that transform from this noise distribution through parameterized convolutional layers to an output of hopefully a porous media that we're trying to model with our GAN generator. If we consider some of the results here, you can see on the left-hand side one of the images from our training database, and on the right-hand side a GAN example. And as we're going to fly through these cubes, you can see that many of the features that we see in these real images are also present in the generated samples, and that they really have a high fidelity in the outputs that these networks are able to generate. What's more important, though, is that we can also try to condition these models to observations. Specifically, we might condition them in the image domain to things like thin sections or two-dimensional images, but also if we're going to go to larger scale observations, so this could be at the reservoir scale, well data, for example. And we can do that in a stochastic way by starting at random positions with our latent space, and we minimize some objective function to end up in a subspace that characterizes and honors these observational data. And here I'm just going to fly now through one of these latent spaces, and you can see this porous medium transforming between realizations that all should honor the data distribution and our samples from our porous medium, if you will. So at the reservoir scale, just to give you an idea of some of the work that we've done here, this is a three-dimensional GAN again, but now trained on a reservoir model from Marietos, where now we try to condition this GAN generator to an observation at a well location, which is right at the center of this cross-section that you can see here in the top-down view, and also a single realization in the cross-sectional view. And here we've conditioned 1,000 realizations to the same well data. And what we see, especially on the standard deviation, is that these realizations that have been conditioned to that data honor all the data at the wells, and the way we see sort of higher variances occurring due to the randomness of these realizations away from the well data. And this is what we would, of course, hope to see. But individually, they still honor very much the structures that we see within this reservoir model. So I've showed to you that we can condition to data at the image domain, but can we also condition to other data? And here, what we've done is we've introduced a framework, a Bayesian framework that allows us to use these GANs as priors on parameter fields in physics-driven inverse problems. And specifically, we're going to make use of the fully differentiable nature of these deep neural networks in a Bayesian inference setting that also leverages gradients of the forward problem. So we're going to represent our prior distribution with a GAN that is going to output geological models, if you will. We then have a likelihood that contains a numerical forward solver. Of course, we're going to need some observations to compare against in the problems that I'll show to you. These might be seismic data or production data, so dynamic flow data, pressure data. And then what we want to have is, of course, the posterior distribution over the geological models that honor the observed data and also our prior distribution of the geological features that we're representing with our GAN. And the way that we're going to do this is leveraging also gradients from the forward problem using the adjoint state technique. The examples that I'll show to you, though, they are using two-dimensional GANs. And again, here is an example of what these networks look like. But now we're not considering these three-dimensional porous media, but rather these two-dimensional reservoir models. And specifically, it's also possible to output not just individual, let's say, images, but we can also output multiple parameter fields. So here, for example, we're generating realizations of the facies probability, properties of the material, such as the permeability or porosity, all at the same time, and which are being modeled at the same time in a stochastic way by these deep generative models. Specifically, in this inversion example that I'll show to you, I'm going to consider a full waveform inversion problem. So what we have is the generative model embedded in a two-layer system with an acoustic source or multiple acoustic sources that create acoustic waves. And we measure the reflected waves and the back at the surface. And we're going to try and invert for the subsurface properties, the P wave velocity, but also the facies, by performing this, by solving this inverse problem. And specifically here, we use an approximate inference technique that actually is very similar to the gradient descent method. We're going to start from a random position in our latent space, here denoted by ZT. And then we have two terms. One is the contribution from the observations, where we can compute gradients of the mismatch of the data with respect to the output of the generator. And then we can further back propagate that mismatch to our latent variables, allowing us to obtain a gradient with respect to the latent variables in our current iteration. On top of that, we also have to add some noise because this is required in the Bayesian inference technique specified here, which is called Maja. So we do that in an iterative way, and at the end, we hope to get a sample from the posterior distribution that honors our observations. If we perform that task, we use a framework that leverages PyTorch and DeVito. We can see that the mismatch of these samples is actually very small, so less than 5% error. And if we consider just looking at a variance map of the unconditional prior, you can see everything in white, so everything is completely at random. But as we introduce acoustic information from a number of acoustic shots at the surface, we can see that these geobodies are being more and more constrained as we increase the number of available acoustic information into the system. And so if you take the reference model here, we can start to see these halos of the geobodies being inverted for with a higher probability or smaller variance also at the location where these geobodies keep popping up in the posterior samples that we obtain through this method. Now you might say, okay, if you're more interested in the porous media domain, then this might be an example that is really for you. And it's a nice visualization of this computational graph that we're actually leveraging here. So in this example, we're going to inject water into an undersaturated oil reservoir, and we're going to now model the facies, the permeability, and the porosities in the subsurface system. Just to highlight here of how the flow of information works is that we sample from our prior distribution initial starting point. This gets transformed through our generator and ends up with a realization of the subsurface of what it could look like. So from our prior, we then forward model that with a reservoir simulator from MRST, which is also a joint enabled. With that, we can actually compute a gradient with respect to the underlying properties based on the observed mismatch. And then we can further back propagate this mismatch into the latent variables and make a small gradient step, or using our Maja inference technique to move further to the posterior distribution of our geological models. And if we consider the evolution of these models in time as we go through this process, you can see how this inference scheme where we are now seeing all the underlying geological models, actually honors not just the dynamic data, but also the semantic shape of these structures, and really tries to sort of place geobodies to obtain a dynamic behavior that is geologically consistent and consistent with the dynamic data observations that we have. And just to highlight, if you consider on the top just prior samples from the GAN and the corresponding dynamic responses, we see quite a big spread, especially on the pressure behavior. And if we consider the posterior ensemble of resulting models, that these actually honor quite well the production data that we observe here, and we can also at the same time condition to well data at the boundaries of this reservoir model. So the first work that I presented, we're extremely happy that this was also awarded the best paper in 2020 in mathematical geosciences for the work that we did along using GANs for seismic inversion and using them as a geological prior. So we're incredibly honored to receive that award. I do want to leave you with a couple open questions, which I think may inspire people to continue to work in this field. Of course, there's always the question of how can we measure how good these generative models are? How can we make these methods for inversion more efficient? There are many different generative models that we could consider here to work with. I mentioned things like self-normalizing flows, and right now it's not clear whether GANs are even the best way to solve this approach. So there's plenty of room to explore. And ultimately, we want to find also some guarantees for convergence of these methods. There's some really interesting groups out there to follow. During my PhD, Eric Laloy and his co-authors did some excellent concurrent work at the Belgian Nuclear Research Center. There's Michael Perch and Alex Dimakis at the University of Texas at Austin. And I'm also extremely grateful to TotalEnergies in Houston, Saclay, and Pau, who have been very supportive of the work that myself and my co-authors have done during my PhD. So just to give you an outlook, all of this work was done up to 2019, and I just want to show what these GANs are able to do today. On the right-hand side, you see the most recent version of sort of the state-of-the-art of these GANs, created by NVIDIA and Aalto University by Karas et al. And for anyone that's fascinated by outdoor scenery, porous media in the wild, if you will, it's incredibly spectacular to see what these networks are able to do and the samples that they are able to generate. The coherency in the images is really stunning and mesmerizing to watch. So plenty of more things to look out for. I do want to make a quick plug of my current employer. I mentioned that formerly I was at Imperial College. Now I'm working for a company called Earth Science Analytics. We are a Norwegian startup. I get to work with extremely great partners from the energy industry and from technology, working on subsurface machine learning problems and developing new technologies in this space. If you're interested, and if you're a recent graduate or a postdoc or someone who wants to join an R&D in industry position, we are hiring, so please do reach out. We'd be happy to have a conversation with you. So with that, I'll leave you with some references. You can find all the code available online, and all the papers have been published under a permissive license. So thank you again for having me here today, and it was a pleasure to be here, and I'd be happy to take any questions you have. Thanks.
Thank you, Lukas. It was really, really interesting. It's impressive to see like the tremendous development that's happening in this field, right? To feel like this tremendous energy all input into deep learning and all the applications. Do we have any questions, or if people in the audience, you are welcome to put questions on the comments on the right side of your field. Do we have any questions from the studio here?
Well, I have one question for you, Lukas, with respect to the first part of your presentation. This is more like a open question. So, where do you see the field of generative models for porous media going further? What do you envision for the future?
Yeah, it's a good question. I think there's plenty of room, especially in materials design. I think there's actually been some work also at Imperial while I was still there, where people were looking into creating better batteries, designs for batteries, cathodes. And one of the interesting things that these generative models, not necessarily GANs, but also other deep generative models, is that you can steer them in a way with these external forcing terms or gradients, if you will. And so what you could use these generative models for is trying to optimize, for example, materials, and trying to understand which structures are optimal for certain tasks. Maximizing the capacity of batteries, I think, is one. But there are plenty of other material properties that we're trying to optimize in that domain, where I think that could find some application. So that's at least one area which I think could be quite successful and interesting in the future.
So do you see the field of differentiable simulators impacting all these applications?
Yeah, I think so. Especially, I mean, if you look at, there's sort of a concurrent field of these physics-informed or physics-coupled machine learning going on, where people are now actually realizing that you can combine these differentiable physics solvers with machine learning. I think if you consider there things like computing the electrical resistivity or having some kind of simulation of a physical problem and then trying to optimize those properties by a physics-informed system, then there is definitely room for combining these simulators with these differentiable representations of the materials. And I think in the adjoint PDE world, this is already something that has been done to optimize materials or optimize underlying property fields. But the interesting notion here is that you're sort of constraining the space of possible solutions to the ones that honor some prior understanding. And I think this is quite powerful.
Yeah, no, I agree with you, and it's exciting to talk about what the future will bring.
Yeah, absolutely.
Super.
Yeah,
I have another quick.
Sorry.
Go ahead, Sarah.
Yeah, I have also a question, but more technical one. I mean, so it was a really interesting talk and a really interesting topic, and I was wondering about the computational cost of solving the adjoint problem.
Yeah, right. It's still an open problem. I mean, the method that I present here is not intended to solve the computational problem of the forward problem. This is actually something that I had to live with in a way. If you don't have a fast forward and a joint solver, then of course this can take significant amounts of time, especially if you consider three-dimensional problems. You need a good system that allows you to compute these adjoints. There are some efficient techniques out there. And one thing that I left open for, at least in my thesis, is that one can also consider sort of approximations to the forward problem. If there are ways to sort of accelerate the forward solving part and the adjoint, this is still something that I think is extremely useful to work with for a practical setting, because the computational runtime of these methods is pretty long. To get even one sample out of the posterior can take quite a while. And if you have any way to accelerate that, then I think this will be extremely useful. But for me, the main focus was to try and sort of bring these two worlds together. And then I'm sure there will be plenty of other people that can try to optimize in that space.
Yeah, thank you for your answer.
We have a quick question from Kamal here on the background in the studio.
Yep.
So he asks, what are the restrictions or the challenge towards 3D models?
Yeah, I think usually the 3D models suffer from, let's say, more the engineering challenges. So first of all, these neural networks are usually already quite big. And back in in 2017, when I started working on this, most GPUs had around 10 gigabyte max of GPU memory. Today, we're seeing models that go way beyond that. There are also better computing infrastructures. But 3D convolutional neural networks require a lot of memory. And on top of that, you usually also need good training data and enough training data to actually train these models. So in the example that I showed, there were a few thousand of subvolumes that we extract from the micro-CT images, from much larger micro-CT images. The same for the reservoir models. And you need somehow to be able to represent the training data. So for 3D reservoir models, creating a good training set of 3D reservoir models in itself is not a solved task. I think if you do something like object-based modeling, then you can sort of create a bunch of good training data sets for training a 3D GAN. But anything that is more realistic or sophisticated, like process-based models in geology, generating that training data set is going to be a significant computational task on its own. So that's, I think, a big challenge there.
Right, thank you. And just a final comment from Martin here. It's always a pleasure to hear your presentations. And of course, we all share Martin's opinions with regards to that. So I think now we can finish the session and move on to our next speaker for today, which is Federico. So Federico is a PhD. Federico Lanza is a PhD student in theoretical physics in a joint agreement between the Laboratory of Theoretical Physics and Statistical Models in Orsay, France, and PoreLab, the Porous Media Laboratory in Trondheim, Norway. Research focuses on understanding the flow of non-Newtonian fluids in porous media. And he employs tools from statistical mechanics as well as numerical simulations. So Federico, the floor is yours. And share your screen.
Thank you. I shared, but there is an
issue,
I guess. Oh my God. Trying to figure it out.
No,
maybe I may have pressed something. Maybe I can share again. Okay.
Sure. No worries.
Okay. I have. Sorry.
Oh, it's okay.
No problem.
No. Okay. So. I think now you can see.
Yes.
Okay, very good. Okay, thanks for your nice presentation, Marcel. Before starting, I just want to say that this work I'm going to talk to you today, that you can find as a preprint on this underlying archive code, was done not only by me, but with the help of, with the contribution of both my supervisor, which are Alberto Rosso and Alex Sanz, respectively from LPTMS in France and PoreLab in Norway. And also with the help of Laurent Talon from FAST in France. Okay, I introduced the topic talking about an experiment that was done in the 19th century by a French engineer, Darcy. Historically, represents probably one of the first experiments that was done for fluids flowing in porous media. He basically took a column of sand, like the one that you found pictured here on the left. He poured some water on the top of the column. He applied a pressure drop with a piston on the top of the column, and he measured the amount of water outgoing from the bottom of the column per unit time. And he found that the pressure drop is, or better, the volumetric flow rate is directly proportional to the pressure drop applied. And this law, the so-called Darcy law, it was found later that it's valid not only for Newtonian fluids, but for not only for water in sand, but for any kind of Newtonian fluids in any kind of coarse material. While this is not valid anymore for non-Newtonian fluids, which are fluids that basically behave in a non-linear way, so present a non-linear dynamics. In particular, Darcy law can be considered valid if we take Darcy law and we implement two modifications. First, in general, the linearity is not valid anymore. So Q, the flow rate, can be seen as a power law of delta P, the pressure applied, where the exponent beta is not 1 necessarily, but can be of any value, positive value. Second, the system can present a pressure threshold, namely, if the pressure applied is smaller than delta Py, the pressure threshold, no flow occurs. So the system behaves like a solid. While for pressure greater than delta Py, the fluid starts to flow. And we will call from now on ill stress fluids all kind of Newtonian fluids that present a pressure threshold different from 0. So what about our work? Our work aims to study what happens when we take capillary tubes and we fill it with a Newtonian liquid like water, and we inject some small bubbles of ill stress fluid that present this ill stress. And we try to study the fluid dynamics of such a system. We start first with the fundamental brick, namely one single capillary tube and one single bubble inside. And then we extend the study to the one of fiber bundle. Fiber bundle, which is a model made of several capillary tubes and can be considered as a rough but still a starting point, starting approximation of a porous material, a starting point for further studies for more realistic porous models. Since we assume that the follows power law of the difference between the pressure drop applied and the pressure threshold, our goal basically consists in finding a value for the pressure threshold and the exponent beta for different tube geometries. The basic assumption here that will be valid for all our work is that both fluids, the Newtonian background and the ill stress drop, or we can call it also bubble, are both immiscible and incompressible. In this way, the surface separating the two faces will remain stable during the evolution of the system. Okay, let's start talking briefly about the simplest system possible, which is a single bubble injected in a single tube that presents a constant radius. In this way, both the pressure threshold and the exponent governing the flow rate depends on the characteristic of the fluid that composes the bubble. So even if the bubble is small, they both influence the pressure threshold and the exponent. In particular, the pressure threshold will depend on the ill stress of the fluid composing the bubble, while the exponent will depend on the flow index. They are both characteristic typical of the fluid that compose the bubble. And we can see that the power law is 1 over n plus 1, and it's not trivial. So in general, it's not 1. And for pressure close to the for applied pressure close to the pressure threshold. Instead, if we consider again a single bubble in a single tube, but with a non-uniform radius, such that the radius is parameterized by the function that you can find on the top left of the slide, even if the modification is small in modulus, the contribute to the pressure threshold will be not given anymore only by the pressure, by the yield stress of the bubble, but also on the surface tension that emerge between the two surfaces separating the bubble from the surrounding Newtonian fluid on the left and on the right. Moreover, the pressure threshold will depend on the position of the bubble. More precisely, it comes out that the pressure threshold can be seen as a maximum of a function that we call gamma along the tube, the maximum of a function gamma that depends on the position of the bubble, and the maximum value that this function gamma assume along the tube interval will give the pressure threshold. And we can see that it strongly relies on the position of the bubble. And if we compute the flow rate averaged over from 0 to L over the tube length, we actually see that the exponent has changed, is similar, but not equal to the one of the uniform tube case. Instead of having 1 over n plus 1, we have a 1 over n plus 1/2 in the limit, again, of pressure applied close to the pressure threshold. So for small pressure difference, basically. So far, we talk about single tubes, trying to stay generic for generic geometries, uniform and non-uniform. What happens if we consider a system composed of several capillary tubes put in parallel, namely in which we apply the same pressure at the edges of each tube, so the so-called fiber-Brandão model? Well, in general, we expect that if we inject several bubbles in each tube, for example, the same number of bubbles in every tube, the bubble can be the number of bubbles in every tube can be the same, but the position can vary in general, like it is shown in the picture on the left. And since the position of the bubble can vary from tube to tube, also the pressure threshold that depends on the configuration of the bubble position can vary from tube to tube. And if we suppose that the tube, if you suppose that every bubble can assume a position along the tube, can assume any position with equal probability, we actually can compute the probability that a certain tube presenting a certain configuration of bubble position present a certain value of the pressure threshold. And in the limit of many tubes, this corresponds to calculate a probability density function for delta Py. This probability density function allows to compute the average flow rate of the fiber bundle. Can be seen as the sum of the flow rate of every tubes, that, or better, the integral of such a single tube flow rate multiplied by the PDF, by the probability of that tube to have that value of delta Py integrated over all possible values of the delta Py. And in general, the domain of this PDF can vary from minimum value to plus infinite in the limit, of course, of many bubbles. So far, we've talked about generic shape, generic non-uniform shape of the tubes. Let's try to focus then on some simple geometries. Let's start from a sinusoidal shape. So parameterized by the equation that you can show on the top left and that I schematize in this sketch on the top right of the slide. In this case, since the sinusoidal function is easily manageable with respect to other more complicated geometries, we actually managed to find an analytical form for the PDF of delta py that will whose domain goes from the sum from the pressure threshold given by the yield stress times the number of bubbles, and goes in general to infinite for the limit of many bubbles, and it can be seen as the product of Gaussian and a linear factor. And we try to confirm this analytical prediction, simulating a system in which we take a sinusoidal tube, we randomize the position of 1,000 bubbles. We set some values for the parameter of the values of the pressure contribution, and we compute for such a tube the corresponding value of the pressure threshold. And we repeat again for several tubes, generating several different random bubble configuration of the position. And we then plot the histogram found from the values of delta py collected, and we can see that in the limit of many values of delta py, we actually find the analytical prediction with a very good overlap of the two. And again, the average flow rate that we now can compute thanks to the PDF of delta py is again a power law with an exponent which is again non-trivial and different from the one that we found before for the single tubes. Now, so far we talk about an analytical shape of the bubble, but what if we consider a non-analytical shape? In particular, we focus on the triangular shape that is parameterized by the equation that you find here on the top left, and presents in particular some points, some cuspids, points in which the function of the radius as a function of the position is not derivable. In this case, for a single tube, the pressure threshold can be seen again as the maximum of a function gamma along the tube. But this function gamma is not analytical anymore and can be seen, this is the particularity of a triangular shape, as a stochastic process of n steps, where n is the number of bubbles, along L, so from 0 to L. So finding the pressure threshold is actually corresponds to find the maximum of a stochastic process. So if we want to find something about the probability distribution of such a aleatory variable, if we have to find something about that, we have to look at what the stochastic process theory tells us about this behavior. And the stochastic process theory says that actually the distribution of a maximum of a stochastic process in the limit of small values goes as a negative exponential function regulated by the Hurst exponent, which is an exponent typical of that particular stochastic process. And so the probability distribution in that of delta py in the limit of delta py close to the minimum possible value follows that distribution. We try to simulate this system in the simplest system possible, in the simplest case possible, which is the one of Newtonian bubbles. So the bubbles are Newtonian, and only capillary forces contributes to the pressure threshold. And in this particular fortunate case, the gamma function is a stochastic process. In particular, is a Brownian motion. characterized by h equal to 1/2. A typical trajectory of this function is shown on the plot on the left. And in particular, it comes out that is a Brownian bridge, so a Brownian motion that starts in the same points where it ends. And while on the right plot, we actually try to simulate the maximum, an histogram of maximum of this Brownian motion. And we actually see that for small values, the asymptotic value described by the exponential prediction is actually confirmed. So in this limit, again, we find a good agreement with the theory. So far, we reached our goal, meaning that we actually find some values for delta py and for the flow rate, for the power as seen as a power law, both for a single tube or for a bunch of parallel tubes, and for different geometries. And of course, that was a theoretical work and experiment that may confirm or not our prediction are desired in the future, and as well as all other numerical simulation that we haven't done and can confirm and give strangeness to our prediction. Thanks for your attention. That was actually my first work that we managed to publish on Archive. And but if you have any other question, you can contact me on this mail address.
Okay, thanks for your great presentation, Federico. I'd like to invite the audience to type your questions in the text box on the right-hand side so we can have an interactive session. And so, meanwhile, I can start with a question from my side. So, have you evaluated the flow in interacting tubes? I mean, when they are not isolated tubes? What do you expect to find in a situation like that?
You mean interactive tube?
Yes.
Actually,
not isolated one.
Yes. Actually, this will be the following step. We focused on parallel tubes because fiber bundle model is a good, I mean, it can be sometimes a good approximation. Of course, is a starting and a rough approximation that actually, but that may gives us some hints. But since it's simple, we start from that kind of system. And actually, my thesis, PhD thesis, will be about studying two-phase systems, Newtonian and non-Newtonian, in as realistic as possible models.
Okay. Yes.
I have a quick question.
Yes,
Federico, just could you just remind me again what is the n, the small n that goes in the exponent between the flow rate and the delta p?
The flow rate.
Just get back to your slide number. Let's see, number 5 maybe.
Okay. You mean the the constant?
Okay. So what is the flow index?
The n. Okay. I introduced these two values, both the yield stress and the flow index, as values, parameters characteristic of that particular fluid. And indeed, they are, of course, in the sense that they characterize their dynamics. In general, if we modelize such a non-Newtonian fluid with power law between the shear stress and the shear rate that we can, the shear stress that we apply and the shear stress that we observe, the flow index is the exponent that regulates the shear rate as a function of the shear stress. or also contrary, it depends. Of course, in that case, it becomes 1 over n.
Okay, so
The
it's
E
connected
stress
to the
is
rheology.
basically the stress that you have to reach in order to the fluid to flow. So it comes from the they actually, both parameters come from the constitutive equation, which is actually the Hershey-Berkeley equation.
Right. Thank you.
Great, great. So let me see here if you have other here. So meanwhile, I guess I also have another one as a curiosity, and because you mentioned about the non-linearity of the flow regime, and I guess it might be attributed to the fluid properties and also to the pore structure, and actually to your tube shape, yeah. And so have you evaluated also the influence of the fluid flow rate, not only on capillary forces but viscous forces? And I'm not sure, I guess, have you evaluated that?
Well, we can see that we can think the yield stress contribution, for example, to the pressure threshold as a contribute. No, how to say? The point is that to compute, for example, the flow rate, we actually evaluated the pressure drops along the tube as a contribute of both viscous forces in fundamental, then from the viscous contribute to the flow rate, and also the pressure drop provoked by the surface tension. So actually, we compute at the surface of the bubbles the surface tension contribution. And for a constant for a constant radius, it comes out that this contribution is 0, but this is a fortunate case, while for a non-uniform it's not 0. And for the other parts, for the other drops, the viscous contribution is the fundamental one. So in this way, we take into account both contributes.
Okay, great. Yes.
So it's implemented in the equation, actually.
Okay, awesome, great. And so I don't see any further questions. And so great. If you don't have any more questions, again, I want to thank you, Federico, for your talk. And I also want to invite you for our next tea time talks. And do we have the final slides, please? Yes. So it will be on 3rd of November at 5 p.m. Central European Time. And Anna is from Australian National University, and she will talk about the evolution of sandstone's wettability during supercritical CO2 brine injections. And as soon as we have the information from the second speaker, of course, we are going to share it with you as well. And so with that, we appreciate your participation and see you in the next 2 weeks. Bye bye.